Swayam Prabha. Digital India. Educated India.
Which can be further simplified as, so if I multiply this matrix with this, what do I obtain? Okay, so now equating all the elements, what do I get? So I can have four equations from these four four individual equations from this matrix equation. So the first, let's see, consider this one. So this expression and this expression should be equal to 1. So we have okay, so this to cancel. From here we have magnitude of S11 is equal to magnitude of S22. Now note that how many unknowns are here. So here we have from 4 S parameters we reduced. Because of reciprocity, we now need to know only 3 S parameters, but then each parameter has an amplitude and a phase component, so there are 6 unknowns. Okay, so this is one other relationship. Okay, so we have reduced the requirement for another one unknown, and then if we substitute, so again coming back to say this relation, so from here we get S12 magnitude is equal to 1 minus S11 whole square. Okay, so again by this relation we have reduced one more unknown. So now instead of 6, so with this we had 5 unknowns, now with this we have 4 unknowns. Okay, now further, let us say we can write S11 like this. And say we are writing S12 like this. Okay, so now if we substitute, if we consider this expression and equate it to 0, what do we get? Let's see. So we have S12 conjugate S11 S12 conjugate plus S12 S22 conjugate is equal to 0. Now substituting these expressions in this equation, what we have is okay, so from here we can write one expression like e raised to j theta 1 minus theta 1 2, and that is equal to minus e raised to j theta 1 2 minus theta 2. Okay, so then this is equal to e raised to j pi plus theta 1 2 minus theta 2. So from here, if we equate the left hand side and right hand side, we get from here we have theta 1 2 is equal to theta 1 plus theta 2. Okay, so 2 theta 1 2 is equal to theta 1 plus theta 2 minus pi, and this we can then generalize to any odd multiple of pi, from which we can write okay. So this way another, so we had four unknowns. Now with this equation we reduce the number of unknowns by another one, so now we have three unknowns. So what are the unknowns that we need to know? One is the magnitude of S11. So from the magnitude of S11 we can know the magnitude of S22 and also S12. So all the magnitudes can be known, magnitudes of all the S parameters of the two-port network can be known from modulus S11. And the other two that we need is theta 1 and theta 2. So from theta 1 and theta 2 we can find out theta 1 2, and that will give us all the information for all the parameters. Okay, so now let us see how we can calculate S parameters directly. So one way to calculate S parameters, as we saw while discussing the relationship between Z and S parameters, recall we had derived a formula, right? So the problem that is given is how to find out the the S parameters of a system, of a network. How to find out the S parameters of a network if we know the Z parameters. So this relationship, recall in the last part we had derived two relations. Okay, and another relationship was Okay, so using these two relationships, we can find out S parameters if you know the Z parameters. Now Z parameters, you know, right? We can find out how Zij was defined. It is Vi upon Ij, and with Ik equal to 0, K not equal to J. So this is quite simple, right? So to make all the other IKs equal to 0, all we have to do is keep those ports open, right? So that's why, you know, Z or Yij, they are somewhat easier to calculate. So for example, Yij is defined like this. Okay, so all VKs, the voltages at all ports other than J should be equal to 0. And how to make that 0? We just short those ports. Okay? But S parameters are defined in a different way, right? If we directly want to calculate S parameters from first principles, so the definition of Sij is Bi upon Aj, a k equal to 0, k not equal to j. How do we achieve this? How do we make the incident voltage waves at all ports other than j equal to 0? So to do that, let us consider a simple circuit. So the simple circuit that we will be considering is just a series reactance. Okay. Now, so there are two ports, port 1 and port 2. Say I want to obtain S11. So S11 is given by B1 upon A1, right, with A2 equal to 0. So A2 flows like this and B2 is the reflected wave like this. So how to make A2 0? How do I ensure that A2 is always 0? So Z1 and Z2 are the characteristic impedances at port 1 and port 2. Again, these can be arbitrarily set. Okay, since in this case there is no transmission line, so there is no the way we had defined characteristic impedance for a transmission line as depending on the inductance and capacitance per unit length, that is not available here. So we can arbitrarily assign the characteristic impedance at port 1 to be Z1 and at port 2 to be Z2, and the S parameters that we will be deriving will be for this particular configuration, that is when characteristic impedance at port 1 is Z1 and at port 2 is Z2. If we change, for example, if we make both the characteristic impedance at both the ports equal to Z1, then we will obtain a new set of S parameters. So now coming back to the question, how do we make A2 equal to 0? So to do that, suppose we connect impedance which is equal to the characteristic impedance at port 2. Then we know that the reflection coefficient, so gamma L, which is equal to Z2 minus Z2. So let me elaborate this. Gamma L is equal to ZL minus Z2 upon ZL plus Z2. Now in this case ZL is equal to Z2, that's why gamma L is equal to 0. So any wave that is incident on this load would not be reflected back. Okay, and that's why A2 will be, we can ensure that A2 will be equal to 0. Now in this case, so this A2 equal to 0, this condition can be imposed by connecting Z2 at the output. So after that, then this S11 is nothing but gamma in. So if I just calculate the input reflection coefficient at this point, then that must be equal to S11, because for this configuration A2 will be anyway 0. Now what is gamma in? Gamma in is equal to Z in minus Z1. Here, since at port 1 the characteristic impedance is Z1, so this will be this is Z1. Now what is Z in here? Z in is this impedance in series with Z2. So this is nothing but Z2 plus Jx minus Z1 upon Z2 plus Jx plus Z1, and that is equal to S11 parameter. Okay. Similarly, we can see, from symmetry we can find out S22 will be equal to Z1 plus Jx minus Z2. Symmetry means if S11 is this, then if we just substitute 1 in place of 2 and 2 in place of 1, we should get S22. Z1 plus Jx plus Z2. Okay, so that was about S11 and S22. And then since this is a reciprocal network, since this reactance is a reciprocal element, so this is a reciprocal network, so S12 will be equal to S21. So if we just calculate S12, then that should be enough to calculate S21. Okay. Now from here, if you want to calculate S12 and S21, you can use the relations that we just developed. So for example, S12 magnitude will be equal to S21 magnitude, and that will be equal to 1 minus S11 whole square. You can calculate the value of S11 magnitude from this equation. Okay. Similarly, so that is about S12 magnitude. Similarly, if you want to calculate the phase of S12 and S21, you can use this relation. Okay. But suppose you want to calculate it from first principles. Okay. So in that case, let us redraw that circuit once again. Okay. Now here, say the current at port 1 is I1 and current at port 2 is I2. Okay, so then we can have I1 is equal to minus I2, right? Now if I write this equation in terms of normalized currents, so then I have okay. Now recall that I1 normalized is given like this. So this is this value and this is equal to but then we saw that A2 is equal to 0, right, because of this matched load Z2. So this is equal to 0. Okay, so then this one is equal to plus B2 upon square root of Z2. Fine. So what did we get? We got A1 minus B1 upon square root of Z1 is equal to B2 upon square root of Z2. Okay. So then if I divide left hand side and right hand side by A1, what I get is now what is this quantity? This should be equal to S21 since A2 is equal to 0 and this is to S11 which we have already calculated. So this implies 1 minus S11 upon square root of Z1 is equal to S21 upon square root of Z2. So then from here we have S21 is equal to square root of Z2 upon Z1, 1 minus S11. Now what is S11? S11 we have already calculated, right? This one. So if we just substitute it, so this is S11. So then this becomes equal to so S12 or S21 is equal to this value. Okay. Okay, so that's how we find out. Now in this case, see the relationship between the currents was simple, this one. That's why we got it so easily. But then we can have a more complicated network. For example, let's say we have a network like this. So the characteristic impedance here is Z1 and here is Z2. Then how do we do that? So in this case, the voltage here is V1 and voltage here is V2 and here it is V1. So we know that V2 is equal to V1 upon R1 plus R2 times R2 and V2 is equal to V1 plus V1 minus V1 and V2 is equal to V2 minus. Now in terms of normalized voltages, I can write this as Z1 into V1 bar, okay, plus V1 bar plus V1 minus bar, and this is equal to Z2 V2 plus V1 minus bar. Okay, so this is how we can write these two equations, and then using the same principles that we developed, so now we have a relationship between, so what I mean is we can further simplify this as V1 is equal to square root of Z1 A1 plus V1 and V2 like this. And then if we connect a matched load here, that is Z2, then A2 will be equal to 0, so this will reduce to Z2 B2, okay. Then V2, if we use this relationship, okay, then we will get a relation between these two equations, and so we will relate A1 B1 and B2. Also note that because this is a reciprocal network, hence S12 will be equal to S21, okay, but this is not a lossless network, okay. uh, for example, here in the previous network where we had a reactance Jx, so we could use those equations that we developed for lossless networks to find out, for example, S11 magnitude will be equal to S22. We could do that because it was a lossless network. But in this case, since this is a lossy network, we cannot use those relations, and we have to find out the S parameters, that is S11, S22 and S12 from first principles. And so now I have already given you the hint, this equation which relates V2 and V1, so then we will have using these two equations we can have a relation relating A1, B1 and B2, and that way we can obtain a relationship between S12 and S11. Also note that the input here gamma in when A2 equal to 0, and when is A2 equal to 0? When this match load is present. So here this gamma in will be equal to S11. If we consider this whole circuit, this complete circuit, then for this circuit S gamma in will be equal to S11. Why? Because A2 equal to 0, and that is because Z2, which is a match load, is connected at the output. Okay, so I have given you a hint. I leave it as an exercise for you to find out all the S parameters for this network. There are a few other parameters that are used also. So we have already seen Z and Y parameters, which are in terms of voltages and currents. There are some advantages of using Z and Y parameters also. Like for example, if we have two networks in series, so by series I mean they are connected like this. Why do I say that these two networks are in series? Because their currents are exactly the same. Okay. Okay. So their currents are exactly the same. That's why in series. And the overall Z matrix, that is this I say this is network 1 and this is network 2. 1 plus 2 will be the sum of the Z parameters of the individual networks. Similarly, if we consider two networks in shunt, so how can we have two networks in shunt? So if we connect them like this, so here network 1 and network 2 both have the same input and output voltages, and so they are called said to be in shunt. So similar to the two networks which are connected in series, the overall Y matrix of this combined system will be the sum of the Y parameters of the individual networks. Okay. One other important is parameters, that is, so these, before going to ABCD parameters, these are the advantages. Okay, if you have two networks in series or two networks in shunt, then using Z or Y parameters we can easily find out the overall network parameters, and then suppose we want to find out the S parameter of this network, we convert these Y parameters to S parameters. Or say we want to find out the S parameters of this network, we convert the Z parameters to the S parameters. Okay, so now the next is one other important circuit parameters is what is known as ABCD parameters. So ABCD parameters are the parameters which are found out when we have two networks in cascade. So cascade means like this. So we saw what is series connected, what is shunt connected, and now this is cascade connected. Now in microwave devices, as we shall see when we discuss couplers, this is a somewhat important, these parameters are somewhat important actually. The reason being, suppose here the is V1, okay, and here it is V2, this is I2. Okay. So suppose for one particular network, say here my current is I1, voltage is V1, voltage is V2, and current is I2. So for this network, I can write my ABCD parameters like this. Just want to make a small correction here. This I2 will be in this direction. Okay. So these output currents and voltages, these can act as the input of the next network like this. And so the overall, so if I call this like the M matrix, and say this, say the M matrix of this one, this network is M1 and this is M2, then the overall M matrix of the system M1 cross 2 will be equal to M1 times M2. So that is the advantage. We can also have normalized ABCD parameters. So normalized ABCD parameters are parameters that relate normalized currents and voltages, normalized input and output voltages and currents to each other. Okay. We can now discuss the ABCD matrix for sample circuits. One is, say, a simple series inductance, series impedance. So for a series impedance, like this, so here the ABCD matrix is given like this. Please verify this. Similarly, if you have just a simple shunt admittance, then M for this circuit is given like this. For a transmission line, once again, the parameters that we need to completely describe a transmission line are like this. So for this transmission line, the ABCD matrix is like this. So suppose you are given unnormalized ABCD parameters like this, then to obtain the normalized ABCD parameters, note that this A and D are dimensionless, okay, and B has the dimension of impedance, C has the dimension of admittance. To normalize them, that is to get the parameters like this, that is equal to A B upon Z0 C Z0 D. Okay. So there are some more sample ABCD matrices given in your notes. Please go through it once. There is one more parameter that is quite important actually, especially used. We use it in the case of BJTs sometimes, which are known as hybrid parameters. So hybrid parameters are like this. So this was about the discussion. This entire discussion was on ABCD parameters. So now we are discussing about hybrid parameters. So again, let's come back to our the two-port network is very important actually. In fact, we'll see when we discuss filters, we'll see that entire chapter is on filters, which is a two-port device. So two-port device, and when we discuss about amplifiers, there also the two-port network becomes very important. So hybrid parameters are parameters relating parameters relating V1 on I2 to I1 and V2. Okay, so that was all about this network parameters and the properties of the S parameters of two-port networks. So that's all the topics that I wanted to cover in this lecture 7. Thank you.